All right, well, welcome to Unit 8, where we're going to study weather. And we're going to start Unit 8 with Lesson 1, which covers the Earth's oceans and atmosphere. So here we are on Unit 8. Open it up. Notice that on page 422, it says that by the end of this lesson, you should be able to explain how energy provided by the sun causes atmospheric movement called wind. So we're going to learn about how the sun produces wind and what wind is. Okay. The state of Texas states that you need to be able to recognize that the sun provides the energy that drives convection within the atmosphere and oceans, producing winds and ocean currents. So those are our objectives for this lesson. Let's go to page 424. And let me talk you through this. Of course, I want you to highlight what I have highlighted. Okay, what causes wind? Well, first thing you need to understand is that the sun does not warm the whole surface of the earth in a uniform manner. Not all parts of the earth get heated the same. And this uneven heating causes the air above the earth's surface to be at different temperatures. Okay? Now, warmer air is going to be less dense than cooler air. Warmer air, because it's less dense, is going to tend to rise. Cooler air is going to tend to sink. And that brings us to convection. We talked about convection when we talked about convection currents in the mantle that help move the lithospheric plates. And we're going to talk about convection again because convection is just the movement of matter in a fluid due to differences in density. So we're going to have convection currents set up in the atmosphere because of the fact that the sun doesn't heat all parts of the earth the same. Actually, it sends out radiation towards the earth, but there are some places on the earth that are receiving more direct sunlight. There are some places on the earth that have longer days than other places during that time of year. And also, water and land don't absorb heat the same way. So all of those things together are going to contribute to the fact that not everything is going to be heated up in a uniform manner. Okay? All right. So like I said, cold air is denser than warm air and cold air sinks. Okay? This is going to help us understand why we tend to get greater pressures, atmospheric pressures, on colder days than we do on warmer days. In general, if you look back through your weather data, you'll notice that we've had, in general, our pressure readings have been higher through the winter time than they have for the beginning of the school year, the summer. Okay? All right. Now, air moves from areas of higher pressure towards areas of lower pressure. Okay? The movement of air caused by differences in pressure is called wind. Okay, so wind is the movement of air. Why does air move? Because of pressure differences. And the bigger the difference in pressure, the faster the air is going to move. Okay, I might talk about what's known as a pressure gradient. We talked about a gradient when we did topographic maps. It was kind of like the same as the word slope. Okay, because a slope you can kind of think of as a line that connects a higher place to a lower place. It's a slope. It's kind of like sliding down a slide. Okay? If it's a steep slide, then the difference is large. Okay? For topographic maps, that meant a large change in elevation. Here, if we talk about a pressure gradient, okay, that means just the differences in pressure from one place to another. If there's a large pressure gradient, then that means that the difference between high and low pressure is very big, and that's going to cause faster moving air, so stronger winds. Okay? All right. Then we have areas of high and low pressure. The pressure gradients that I've just talked about are what help create movement of air on a global scale, meaning worldwide. Okay? Now, we don't have one gigantic convection cell between, for instance, the equator and the pole. We actually have several convection cells that are set up, and it's due to the speed at which the Earth rotates and things like that. Okay? But in general, if you can keep in mind that air moves from an area of high pressure to low pressure, then that'll help kind of drive what we're going to show you. Okay? At the equator, air is heated more than in other places because, in general, the equator gets more direct sunlight. So air at the equator is going to be warmed, and warm air, remember, rises. Okay? So I'm going to show you with an arrow. Okay? Warm air that comes to the equator tends to be heated and rises. Okay? It rises into the upper atmosphere. It's going to cool eventually as it rises. Okay? And it's going to make its way towards about 30 degrees north or south, depending on which hemisphere you're in. Okay? It's going to eventually sink because it has cooled. It's going to sink at about 30 degrees north or south, like I said. Sink, and then it'll move along the surface back towards the equator. Okay? So this is one convection cell that's set up. Here's its matching convection cell. Okay? So we have a convection cell with warm air rising at the equator. That air moves to either about 30 degrees north or 30 degrees south, sinks at 30 degrees north or south, and then moves along the surface back to the equator where it's heated and recirculates. Okay? Then we also have convection cells between 30 and 60 degrees, and we also have convection cells between 60 and 90 degrees. And you have, if you notice, alternating patterns. You have warm air rising at the equator, cooler air sinking. It doesn't matter which cell you're talking about, but at 30 degrees north and 30 degrees south, these cells that come together at those latitudes, that's sinking air in both cases. Okay? At 60 degrees north and south, we have rising air again, and at the poles, we have sinking air again. Okay? So, equator, rising air. Okay? 30 degrees north and south, sinking. "60 degrees north and south, rising in general. Okay. And at the poles, we have sinking air again. Okay. So you have these giant convection cells that are set up because of the fact that warm air rises, cooler air sinks, and we have this global pattern set up of circulating air. Okay? All right. Why is this labeled low pressure? Because remember, warmer air at the equator, warmer air is less dense. That's going to create less pressure. Okay? Why do we have high pressure labeled at 30 and 60? Because that's where air is sinking. Sinking air, cooler sinking air creates higher pressure. A little bit warmer rising air creates low pressure at 60 north and south. So that's why that is labeled the way it is. Okay, let's go to page 425. All right. How does the Earth's rotation affect wind? Okay, first of all, if the Earth wasn't rotating, then winds would be able to blow in a straight line from one place to another. But because the Earth is rotating, winds are deflected, or they seem to curve due to the Earth's rotation. And this apparent curving of the path of a moving object, whether it's wind or an airplane or anything, the apparent curving of a path due to the Earth's rotation, that's called the Coriolis effect. Okay? All right, and I have a reminder. It says use view of Earth from the North Pole. We'll do that in just a second. Okay. Because each point on Earth makes one complete rotation every day, meaning everywhere, it takes 24 hours to rotate once, points closer to the equator have to travel faster, and so faster, therefore, they have to travel faster than points closer to the poles. I'll show you what that means in just a minute. When air moves from the equator towards the North Pole, it's going to maintain its initial fast speed and direction that it got from the equator. Okay? And if it travels far enough, it will have traveled further than the point on the ground that's underneath it. And that's why, it's part of the reason why we get these curved paths due to the Coriolis effect. Okay? All right. What we get. Air moving from the North Pole to the equator appears to curve to the west because the air moves east more slowly than at a point on the ground beneath it. Okay, for the northern hemisphere, air moving to the north curves to the east, and air moving south curves to the west. Okay, it says air moving from the North Pole to the equator, that would be moving south, curves to the west. Okay, and then it wants you down here to put some arrows in. But let me show you what they're talking about here as far as places closer to the poles don't seem to move as fast. Okay, so here's our lovely little view of the Earth from above the North Pole. Here's the North Pole. Okay, we're located down here in Texas. Okay. So in 24 hours, we have rotated around one time, okay? Back to where we started. And because of where we are, we have had to trace out a circle that's this big. So if you wanted to stretch that out and lay it out, you could figure out what that distance is, okay? And divide it by 24 hours and you'd get the speed that you're going, okay? If we're maybe living in Alaska, let's say we're over here living in Alaska, okay? Rotate once. Okay, it takes 24 hours, but because I'm closer to the poles, I've only gone this much distance, okay? Lay that out, and that's a shorter distance, and take that smaller distance and divide 24 by 24 hours, and you get a smaller speed than you would down here in Texas, okay? And you'd be going even faster if you lived at the equator, because you have to go all the way around in 24 hours, and that's a bigger circle, okay? So that's part of the thing that helps us to understand why these winds tend to curve when they're moving from for instance, maybe they got started at the equator and they're moving north or south to places that the speeds weren't as great. Okay. All right, down here we need to put in our curves. Okay. Your arrows are showing surface winds. The orange would be without the Coriolis effect. So without the Coriolis effect, we'd be able to move straight north or south. But with the Coriolis effect, we curve. And in the northern hemisphere, it's going to look like this. Okay. All right. With that information on these 2 pages, we should be able now to answer the review questions 4, 5, and 6 on your lesson review.